never up, so that the electrons here can be what? Can be moved to the side. Okay. Once you do that, you can see you have higher electron density on the p side. Okay, that's actually inject from the inside. Okay, that's and then that minus the initial one. That's how you get the equations, diode equations. That's what we discussed last night. So here let's have two assumptions. Okay, let's see the diode, right? The diode can be long diode or can be short diode. Okay, what is long diode? Okay, long diode basically that means at very far regions from the junction. You see the junctions here. See, here's the p-n junction. Okay, here's p-n junction. Far away from the junctions. I mean, these positions, in these positions. Okay, the excess carriers delta n reach to 0 in both p side or n side. Okay, so basically, if we have delta p, right, delta p. Okay, I would say delta n because now why we talk about delta n? Reason is that because on the inside you inject what? Example one this is diode, right? Just think about the diode instead of solar cells. You have electrons, right? Inject from the inside and then goes to p side. So you want to see how this electron as minority transport on the p side. Okay, that's delta n. Same thing. You have delta p. Inject what? From p to n. Delta p. Then you want to see how the delta p function at the far end. Okay, that's what it means. Okay, but there's a clear definition there. Okay, if the thickness. Okay, if the thickness. If you see, I have some tones here. Okay, this is thickness. The T means the thickness of n side. Okay, Tn. TP means the thickness of the p side. That's the TP. Okay. Between N and P, you see the junction there. This is the p-n junction. This one is the depletion region. Okay, space charge region or depletion region. Okay. Now let's see. Right, on the p side, as we just said, because you have electron inject to p, so you have what? Electron diffusion length, right? That's called Rn. Okay. On the n side, because you have hole inject to the n side, and then that hole will diffuse. That's called diffusion length of holes. Okay. Basically, you have the thickness of p, and then you have electron diffusion length. You compare them. Okay. Compare them. If the thickness is much thicker than the diffusion length of electrons as minority, also the thickness of the inside is much longer than the diffusion length of hole as minority carriers. And then what do you see? You can assume this is a non-diode. Okay, why? Because the diode is so long that electron hole cannot diffuse to the contact. Okay, they cannot diffuse to the contact as minority carriers. That's why they are called non-diode. It's too long for electron hole reach to the contact. Okay, so with that you can see the typically the diffusion length equal to what? Diffusion coefficient multiplies the time. Then that product you take a square root, right? You take the root of that. That's what you get. Okay, you take the root, not square root. Take the root of that. That is the diffusion length of electrons in p side, and then do the same thing dp twice p. Their product, and then take the root, get the diffusion length of the hole. So basically, I think we probably talk about this. I don't recall if we discussed this. Okay, so basically, you see what? Okay, let me go back to the diode again. Okay, you look at the diode here. You have what? You have the right. You basically has the hole diffuse to these directions, right? And electron diffuse to these electrons. Okay, that's basically so you have two diffusions. One is what? One is look at Na. Na that's just the p side, right? You have acceptor, right? On the p side, you have what? You have n because electron diffusion, right? So this part is for here, okay? Then this part is for the n side, okay? Because if nd is dollar, right? Only the p type has. I'm sorry. Only the n side have the dollar because you take a lot of electrons, right? That's the N-type doped. Now on the inside, they have, P as Hall transport, right? Hall diffuse. That's the diffusion. That's why, you have two tones. You have, diffusion current for electron, diffusion current for Hall. You add them together, right? That will be, give you what? Give you the saturation current. Okay, the saturation. That's what it is. And then on this side, basically it's what? They tell you when you add bias, right? See here, when you add bias, that's how much extra, when you add bias, basically your electron concentration will increase, exponentially. That's why it's exponential, right? And then you still have the, what's saturation current? You basically, minus the, minus that. Yeah. Why is that? You can think this way. Look. So this N, right? This is positive, positive, positive. This is P, negative, negative, negative. In the what? In the diode, right? You have the electrons. You go these directions, right? But inside here, inside the what? Inside the space charge region, if this electron, they go this direction, because the electric field is what? It's pull them back, right? Electric field pull this back. You know? That's why this is negative. Okay, this is negative. That negative basically means the what? The current happens inside space charge regions. Space charge region, you have built-in potential. That built-in potential will, push the charge back. So with that, I think we can understand the diffusion current, right? Okay, we understand the diffusion current, saturation current, GIAN, and also, VOC. We have a lot to talk about VOC. Let me see, let me go back. We did not talk about VOC. Okay, VOC basically is what? Basically is the EFN minus EFT, right? If I talk about that's okay. We're going to talk about VOC here, okay? In this slide, okay? First, let's see, So as you see, we already see these equations, right? This part is what? Total is what? Called GIAN, right? That's called GIAN. Is the saturation current, okay? And then this part, especially what? When you're bias, right? That's how much, extra, charge, extra current you can get, okay? So there's a definition here. This is GIAN. So GIAN is dependent by what? Depends on this Ni square, intrinsic carrier density, right? For silicon, it's 10 power 10, okay? Then depends on the electron as a minority, right? Diffusion coefficient of electron in p side, and different length of electrons on p side, and then the p side what? Acceptor concentration, okay? The same thing, you also have n side, you have the Hall transport in the n side, there's a Hall diffusion coefficient, and then Hall, diffusion length, and then the dollar concentration. That's what you have. So that's why all this depends, and also Ni square. So that's what you get here. Since Ni square, as we remember, we discussed that before. Ni square equal to Nc, Nv. Nc is what? Density of the state on the conduction band. Nv is the density of state of the valence band. Okay, that Nc multiply Nv, and then multiply this exponential, minus Eg band gap. That's the band gap over Kt. That tells you how big your intrinsic carrier concentration can be. Typically, when the band gap decreases, right, you see you have what? You have higher Ni, right? When the band gap increases, you have lower what? Ni, okay? So now let's look at this equation. This equation here, right? That's equal to here, right? Then since this side, this guy, whenever you prepare your junction, that's actually almost constant, right? Once you prepare junction, it's fixed. The junction, the quality of the junction is fixed. And then if you just assume the junction can be controlled with good quality, then the GIAN will be depends on band gap. Okay, band gap. Okay. Now if you see have three band gap, EG1, EG2, EG3, the band gap increases. You will see what? When the band gap increases, the saturation current, right, decreases. That's why G0, right, G1 will be bigger than G0, G2, bigger than G0, G3 because G3, G2 has larger band gap than G1. Okay, that's it. So why this is related to the open circuit voltage? If you guys still remember, at the beginning of this lectures, right? Not this lecture, the beginning of this week, right? When we talk about the equivalent circuit, right? Equivalent circuit, right? Equivalent electrical circuit of these solar cells. We mentioned this equation, right? This equation. And then we talk about at open circuit conditions. Open circuit conditions, this one. This is open, right? There's no current flow. So all the current flows through what? The diode, okay, through the diode. That's why, you know, this G is 0, right? And then you get this guy equal to JPH, okay? JPH. And then since this one under almost because open circuit, right? Open circuit as open circuit voltage, we'll see it's pretty big. That's almost similar to the gate voltage you add to the diode. So that's diode open, and then this part, then this exponential part is much bigger than one. You can get rid of one. That's how you get, GIAN times exponential equal to what? JPH. JPH. Then move GIAN to the right side and then take a log on both sides. That's a QVA over KT equal to what? Log JPH over what? GIAN, right? And then you divide by what? Divide by KT over Q. That's come to the right. Oh, Q divided by Q over KT, right? Because Q over KT times VA, you divide by Q over KT. That's KT over Q on the other side, on the right side. That's what you get here. So this is your equation you typically can use to estimate your what? Estimate your open circuit voltage, okay? That's why sometimes if you have high recommendation, the GIAN will increase, right? That means VOC will decrease, right? Because GIAN increase, VOC decrease, right? Okay. And also, if the photocurrent, typically the photocurrent, we talk about the maximum photocurrent, that's the sunlight that noontime gives. Okay, we don't use very small photocurrent, otherwise the VOC can change with the open circuit. The VOC will change if your nighttime is so small. Okay, so with that, you see this one is JPH over GIAN. Take log, that's basically GL, right? Log JPH minus log GIAN, that's here. Okay, and then remember GIAN here? GIAN, as we just mentioned here, remember these equations I talked about? Okay, get this equation here. Okay, and then because it's what? It's a proportional with E power minus EG over KT. So we just assume that the coefficient is C, right? You can see GIAN equal to C times multiply this E power, exponential minus EG over KT. Then with that, you can modify this, you plug that back here. That's minus log C plus EG over KT. Okay, now you see something interesting here. Okay, you see this, you rewrite this equation here, you will see the band gap divided by the Q minus the KT over Q, and then multiply log C minus log JPH. Okay, you see here, it's constant, right? You can see EG minus EG divided by Q over K. Okay, now you see what we find that, the open circuit voltage, the VOC is related to the band gap. Okay, that's something I think we probably talked about earlier. When we discuss, right? When we discuss what band gap is the best, for solar cells efficiency, why the band gap is 1.4? That's because of reason. You have to have reasonable, VOC, because VOC depends on band gap. If you have too small band gap, you will see the open circuit voltage will be very small. That's why it's not good for your solar cells. Okay. That's why the VOC actually relate to what? Especially this guy, the band gap. Okay, band gap determine VOC. Higher band gap typically have higher VOC. And then let's see if that's true. Okay, now let's take a look at the band gap. These are the common materials people use to fabricate solar cells. You see, germanium have 0.6 EV, right? Silicon has 1.12 EV. Cadmium telluride 1.4, and gallium arsenide has 1.45, and the amorphous silicon has 1. That organic guy is pretty, pretty big there. Okay, the 2 EV. Okay. So overall, if you see the, VOC is actually increased, see here, especially for inorganic, right? Germanium, silicon, cadmium telluride, gallium, amorphous silicon. When the band gap get bigger, your VOC is bigger, right? But organic is different because organic take a bark heterojunction structures. You have a lot of energy loss at that junction at that heterojunctions. That's why the VOC is lower. Okay, that makes sense. Okay, so with that, there's the other things you may consider. How what other things can change your VOC, right? For example, the temperature, right, on the environment, right, and also if you want to know the temperature, how the environment temperature, like morning times, the temperature is low, noon times, the temperature is high. That's during one day, and then during 1 month, you may see, like in spring, only of the months, your temperature lower, later of the month, temperature high, and then look at the years, you could say what? Summer, probably your temperature much higher than winter time. And then if you want to care about how the temperature affect the VOC or solar cell performance, you can still take this, equation, because this equation, this is a GIAN, right? GIAN equal to Ni squared. Here, Ni squared is equal to what? Nc VOC, and then E power this. Now you see the uh, now you see the temperature play in fact, because now you have T here, right? I'm sorry. Is that T? Is that T there? Okay. That T actually impact you now, okay? And also not only that T, right? If you take this, you remember the NC equation, that's also equal to KT, the conduction band, electron, effective mass of electrons, right? And the MV will be the valence band effective mass of holes. They also relate to the T, right? You see T here, T here. And then you can assume everything else is constant. It's true, it's constant. Okay, like K pi h bar, right? And then that MC star is also constant. So you can see NC is a function of T, right? C is a function of T, right? And MV is a function of T. Now NC multiply MV is really what? Also a function of T, right? Then that GIAN is the proportional of T, power 1/3, half 3, and then time multiply another T power half 3, and then T power 3, multiply E exponential minus the band gap over KT, okay? That's it. So with that, if I have two temperatures, right? I have temperature 1, there'd be, let's say I have temperature 1 to temperature 2. You can see my temperature 2 will be high. For example, this can be what? Like 330 Kelvin, 300 Kelvin, okay? That's a 300 Kelvin, okay? If that's a 300 Kelvin, right? And you plug that, all the temperature here, we use Kelvin, okay? You plug the Kelvin inside here, 330, you plug another Kelvin, 300 here. See, you can use this equation, you find that about what? Even you only, the temperature, if the temperature only change what? Change 30 times, not 30 times, 10%, okay? From 300 to 330. Now you see the saturation current increase what? By 62 times. 62 times, it's huge, okay? It's huge, okay? And then that's about the GIAN, right? As you know, the VOC equal to what? It's a function of GIAN. When the GIAN is high, VOC is low, right? So that's high temperature, your VOC will reduce, right? So now let's say VOC is T1, that's a 300K. VOC T2 can be, that's a 330K, okay? And then you do the same thing here, you plug in, you can figure out the difference. Typically, if you do this, we will see a T1, we will see a T2, and then there we will see basically this guy minus him, right? Okay, maybe opposite, okay? We should have what? We should have a T2, we will see minus T1, right? Doesn't matter, right? Doesn't this minus here, right? That guy here. Then you can rewrite that equations what? To this, right? To this, okay? Then, here you can see the T2 minus T1 is 1, what happened, right? And then or get again, T2 minus T1 is 2 degree, what happened. So basically, you can just bootstrap, or Excel plot the plot, okay, find every 1 degree temperature increases, you will see decrease about 2 millivolt. That's about, 0.0, right, 0.002 volt, okay? Then it's increase, 10 degrees will be 0.02, right? Okay, 50 degrees will be 0.1 V. That can become very significant. Okay, here you see, the diode, right, can be used as sensor for temperature because you can sense the change of the temperatures. Okay, so yeah, with that, I think here's the very basic survey here. If you look at this, what is the best season for solar cells to operate to have high VOC? This typically depends, right? If you, whatever we talk about here is about silicon. Okay, we talk about silicon cells. But if we don't talk about silicon, it's a different story. So here for silicon, right, you know what? The winter time will be better because the lower temperature is better, right? But this is not true for all solar cells. If we talk about this amorphous silicon solar or the disordered materials, and then the lower temperature will be poor. You need higher temperature because the charge transport is not by band transport, but so many activate process transport. Then that hopping will need higher temperature. Okay, that will be something different. Okay, so what we have discussed so far is about the long diode. Okay, next thing we're going to talk about is the short diode. Okay, the short diode basically, as you know, long diode, what? That is this Rn is what? Smaller than Tn, right? Rp is smaller than Tp, right? That's called long diode, right? So the short diode will be opposite, right? We're opposite. That means what? That means the Rn will be bigger than, okay, Tp, right? Rp will be bigger than Tn, okay? Tn, that's Tn, okay? I wrote something. Tn, okay, right? So basically, my carrier diffusion length is longer than the thickness, right? So all my carrier can pass through the P side or N side, reach to the contact, right? And then you can see your diode is a short diode. It's short diode. There you don't see much loss in the N side or P side, okay? That's exactly the same here, Rn bigger than Tp, Rp bigger than Tn, okay? That's the short diode, okay? So with short diode, we can figure out the similar things. The diode equation is similar. Only things difference here is not Rn. It's called effective, okay, electron diffusion length on the P side, and the same thing here. Effective diffusion length of a hole in the N side. Then the first one is effective diffusion length for electrons in P side. Okay, and then the same thing here as we discussed before. The whole thing here, GIAN, right? The whole thing here is GIAN. That's why this equation is GIAN. Okay, that's a GIAN. That whole thing is GIAN. And then since we have this, Rn EFF, Rp EFF, and the next thing we need to define what is Rn EFF. All right, this is Rn EFF. Okay, follow these equations. Okay, that's basically is Rn multiply what? Coefficient, and that coefficient depends on surface recognition rate. Okay, that's Sn here. Sn here called surface recognition rate. Rn is the same, just what? Electron diffusion length on the p side. Okay, and Tp, what? Tp, you know what is Tp, right? Tp is the signal of the p layer on the p side. Rn, that's what? Electron diffusion length on the n and p side. Okay, the same thing for Dn. That's the electron diffusion length, right? Electron diffusion length. Not the, I'm sorry. Electron diffusion coefficient on the p side. Tp, signal of the p. Rn, electron diffusion length of the p. I can see the same thing would be Rn would be what? Rn would be LP. This one is only Rn, right? That's why everything in this equation is about Rn, because this Rn effective, we call effective, electron fusion in the p side. So everything is Rn. Rn, 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 Rn. Okay. Now if you look about Rp, right? Effective diffusion length of holes in the n side. And then here you will see a lot of what? Rp, right? Rp, 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 Rp. Okay. And then this function here, this called what? This called shine, right? Shine functions. These are cosh functions, right? That's basically what? That's This is a function, right? That's a function. If you know what is TP, what is Rn, you can use that function, calculate easily to figure out what is that effective mass, right? For electron in the p side, for hole in n side. Okay. Then that's see, this is different from the normally we for the long diode we just use Rn equal to Dn times tau n, right? And then you do that product. Rp will be find the product of dp tau p and then take the root of that. This is about the short diode, okay? So with that, here's an example. I think I should, talk about the example a little bit, okay? So in this example, you have basically, P plus N junction, okay? P plus N junction. That's basically, P plus here. N junctions is like this, okay? P plus N, this, okay? Then the problem gave you that the P plus dollar, concentration. I'm sorry, is accepted concentration. That's 10 power 19. And then the electron lifetime in the p side is 4 times 10 power minus 9. And then the Dn electron diffusion coefficient in the p side is 4 centimeter square per second. Then the surface, this Sn, is the surface recombination rate. If you think about short diode, right, when the electron reaches to contact, right, in particular, the contact take electron away, right? But if you think about if you don't have contact there, just assume you to some modern, that's actually you can think about the surface recombination. Any electron pass through, this p type, p side, and then will be recombined, at this surface of this p side. So that's why they're gone, Similar way they're taken by the contact, okay. And then the TP thickness is 150 nanometers. And then on the N side, what you have, dollar concentration 10 power 15, the hole as minority, lifetime, the hole as minority, diffusion coefficients, and then the hole, as a minority, their surface recombination rate, okay, and then the thickness of that N side, okay. With this, both regions, Ni, because this is silicon, right? This is silicon. So whenever we talk about silicon, this is the cell, okay. The intrinsic carrier is 10 power 10. The band gap is 1.1. Oh, I mean, to be more precise, can be 1.12, but 1.1 is enough, okay? And then the conduction band density of state is, times 10 power 19, and then the valence band density of state about 10 power 19, okay? Now the question asks you to calculate the saturation current density, saturation current density, that's basically GIAN, right? GIAN, okay? Then the open circuit voltage, we'll see, okay, okay? Solid cells, then you assume the GSC is this, okay? Also tell you a fear factor, right? And then ask you to efficiency, right? So if you want to calculate efficiency, you know that efficiency equal to what? VOC, apply GSC, apply fear factor, divided by P9, right? Right, okay? Sunlight intensity. Now since the P-light or optical is the same thing, right? Light optical is the same. Maybe I should write optical here. Optical, okay? See, this one is known, fear factor is known, right? Right? And then GSC is known. I need to figure out what's my what? VOC, right? How can you find VOC? You remember at the beginning we talked about, not a beginning, just a few slides before. We talked about VOC here, VOC. That's T, right? The T here will room temperature, right? That's a VOC. That's the equation we're going to use to calculate VOC, right? VOC equal to what? Basically, VOC. The only thing we don't know VOC. VOC equal to what? That's it's a KT Q, right? And log G pH divided by the GIAN, right? Okay. So basically, GPH is very similar as what? GSC, short circuit current, right? Short circuit current. Then KT we know, Q we know. The only thing we don't know GIAN, right? Okay, now we need to find GIAN, right? What is the equation for GIAN, right? This one is GIAN. We talk about two things, right? One is what? See here, if the if it's short diode, That's this equation, right? This follow this equation. Okay, if it's a non-diode, non-diode, non-diode. Let me remove that. This Rn Rp, Rnp, Rnp is the square root of what? Dn, Yn, Rn, Rp is what? dp, yp. That's it, right? Okay. So now the next thing, since we have two equations to find GIAN, right? Either for long diode, short diode, their equations are a little bit different. Now we need to identify what is a long diode or short diode, okay? So in order to determine long diode, short diode, what we discussed here, we need to compare the Rn what with Tp, Rp, Tn, right? Because inside you care about P, on the P side you care about N, okay? So so now we already know what? We already know our TP, our Tn. The only thing we need to know is what? Rn, right? Rp, okay? So Rn is this equation, right? Okay? Rn is this equation. Do we have Dn? We have Dn, good, right? Do we have Tn? We have Tn, good, right? We plug these two back here, you find what is that is, okay? The same thing, Rp, what is dp? We have dp, good, right? We have Tip, good. Plug these two there, so you get this part, okay? And then you compare this with what? TP and Tn, okay? You figure out whether it's long or short diode, okay? Now let's go ahead, see how we can figure out. The first as we just know that we need to what? We need to find whether it's non-diode or short diode, right? So that's why we do this calculation. We find this Rn is this much, Rp is this much, and then Rn compare with Tp, right? It's Rn is bigger than Tp, right? Okay, and then Rp is what? 0.45 centimeters. That's 450 micrometers. That's also bigger than 10. Now you see this one. This is what? Since this length, different length is longer than the thickness of the diode, right? So these are short diode, right? Short diode. The different length is much bigger than the thickness of the inside or P side. So this is a short diode, or the charge can get out. Then the other thing we know, this since this is a short diode, we have to use this function. Use this equation. This equation you have dn divided by na Rn effective, right? dp divided by nd Rp effective. And then since na is what? Go back here. Na is what? Okay, let me remove this. Since the na is 10 power 19, right? And the nd is 10 power 15. So that's about 10,000 bigger. That's why this side can be cancelled, because compared to this tone, this is so small. You can ignore it now. Okay. Since now I ignore these tones, I don't care about RNEFF, right? That's the effective one. Electron different length on the P side, right? So that I can get rid of this guy. Okay. So anything I stay here is a Qn square multiplied dp over nd Rp EFF. Right? And then now you find Rp EFF, since you know Tn, right? You know Tn, you know Rp, you know Tn Rp, you plug here, you figure out that about what? That seems about, let's see, that's some here. That's about this 30.49 divided by 50.56. Okay, and then multiply this, you get this RPFF, right? RPEFF, and I plug back here QNI square multiply that dp, QNI square, right? And you also know dp, right? dp was given to you from dp. You need to use the same unit, right? Or the unit will be centimeter square. Okay, then divided by the air, here is also centimeter. Now you'll be able to get what? Get this GIAN, right? Once you have GIAN, you plug GIAN here. This is GSC, GPH with GSC, and then KT over Q. You know that. You figure out that about what? That about 0.56. 3 V. Okay, more. Then now you have VOC. Get VOC back to this VOC GSC FF divided by what? Right? You get about what? 13.9% efficiency. Okay. So this is just a good, this is a very good example to show how to use equations. It's a short diode, long diode. First, you need to identify whether short diode or long diode, and then once you know that, you know what equation you can use to find GIAN. When you have GIAN, you can find what estimate this VOC. Once you have VOC, you can estimate what VOC. Okay, that's about long diode, short diode. Okay. With that, we already talked about, you know, the equations about short diode, long diode, what's the difference between them, you know. The next thing we're going to talk about, you know, something called recombination in the space charge region. Space charge region basically can also call that depletion region somewhere here, right? So starting point, this end point, you know, that's a space charge region, just depletion region inside the junction, okay? So typically, if you think about what? If you think about diode, if you start to add the forward bias, you can inject a lot of electron to what? To the junction, depletion region. Also inject a lot of hole to the depletion region. That's why, you know, think about this. This is the N side. This is the N side. This side. You inject a lot of N. You inject a lot of hole. What happens in the depletion region? This positive charge, negative charge, you inject inside them, they recombine with each other and they kill themselves. Okay, that's called recombination. That's called recombination in the SCR. Okay, and then you know that, right? Typically, in this SCR is that dope, right? Is that dope, and they have a lot of what positive ions. The inside, they have a lot of negative ions on the p side. You know that you have a lot of defect, right? You have a lot of defects there, right? A lot of extra charge there, and then all of this will help you for the what SRH. That's typically triple cis recombination. That will be happening so quick, so significant, especially if silicon is an indirect band gap semiconductor. Okay. With that, you know, you remember, you know, SRC. This is the equation for SRC, right? We talked about, you know, the site. I don't remember yesterday. We talked about this, you know, recombination and generation, right? Then when we talk about that generation recombination, we talk about SRC. That's SRC equation. So now with that, you know, do integration, I just skip a lot of stuff here. You know, there's some reference you can figure out, you know, how they get that. Eventually you get this current, okay? The current is equal to this. See here? I say only thing you pay attention should be here. E power QV over 2KT, okay? E power QV over 2KT. Then if you take the GIAN out, the GIAN, that's basically this is this. GIAN is something like that. Now you see here, we see N equal 2 because remember E V over NRT, NKT, right? NKT. This here, this is 2KT, right? This is E power QV over 2KT. KT. That's why here we see this N equal 2, okay? This ideality factor is 2. Recombination, because it makes sense because you invert both electron hole, right? That's and then now let's see when you inject electrons, you know, from the inside, this p side, you inject electrons through, you know, inject electrons there. You see, you have what? You have not only the diffusion on the p side, you also have what? Recombination in the SCR, okay, space charge regions, okay. That recombination is the second diode. The diffusion in the p is the fourth diode, okay. The first diode, what you see there, remember, if you still remember the first diode, that's been the diffusion of what? Of holes in the, I'm sorry, diffusion of electron in the p side, right? In the p side. See here? I should go back a little bit because because we need to figure out Ni square, right? We want to see the Q of RT. Okay. See here? You see, and you see here. You see Eg over KT. That's KT is 1 KT, right? Not 2 KT. Okay, not KT. Okay, that's what it means. Okay, now we have two diode. This T1 is, you know, E band gap over 1 KT, 1 KT N equal to 1. Okay, because EG something over NKT, right? So here the recombination EG over what 2KT, so N equal 2. Okay. Now you see we have two diode systems for this diode, right? Once you inject electrons, some will be take the recombination inside SCR. Others will go through what the go through this P type, P side, and then depends which one dominant, right? And then your diode will flow that way, okay? So, but for now, there are two diode systems, right? One is D1, one is D2, right? The ideal case, D1 is N equal 1, D2 is N equal 2, right? That's it, right? This is why you have two diode systems, okay? If you want to figure out, which one dominate at what range of this tensor, what you can do is that you know, you can just plot it, right? You plot this in IV curve, this semi-IV curve. You'll figure out, this slope, whether it's that n is 1 or n equal to 2, right? If n equal to 1, you know what? That, diffusion in the p side dominant. If n equal to 2, you know that what? SCR recombination dominant, okay? So that's pretty simple, okay? Uh, you can also do, you can plot this way, semi-log, semi-log IV curve. You can also do with, the x-axis 1 over kt, y-axis will be the log d naught, okay? And then you can also find the slope. From that slope, you can find out either half eg over half kt or eg over what? Over 1 kt, right? Since the order of kt here, so there will be only kg, sorry, the eg over 1 or eg over 2, right? So that's what it means, because that 1 over kt already on the x-axis, okay? So yeah, that's you can hear. Look. So with that, I think let's see what time now. Okay. Now let's see. We already load the solution current for the long diode, short diode, right? Long diode, and then let's compare them. See, if someone uses germanium to make p-n junctions, make the diode. Okay, others use silicon. Or there may be a third group use gallium arsenide, right, to make a diode, right? Then you'll consider, which one dominant, right? Whether that, recombination dominant or the diffusion dominant, okay? Okay, so now let's first take a look at this germanium, okay? If you look at germanium here, okay? Germanium, right? Germanium has a band gap 0.6 EV, okay? So that's, the EG, right? The EG minus EG over KT, that's about exponential minus 24, okay? Okay, that's a diffusion in the QNR. The QNR basically is what? QNR is the outside the junction. That's the P side is QNR, quansi neutral regions. On N side is also called QNR. It's also quansi neutral regions. Okay, quansi neutral regions. Okay. So what does that mean here? If you look at these junctions, have this. You have this QNR, quansi neutral regions. You have also here QNR, quansi neutral region. Okay, that's it. And then in between this region, called sweat charge regions or depletion regions. So that's QNR basically means P side or N side, right? P side or N side, outside the junctions. Okay. So you see here. Now because you have this, when before you know which one dominant, we have to put them together, right? Your equation should include both G over 1, G over 2, right? And then you can consider since if I have V here, that's not small, then this E power that should be bigger than 1. You can give it 1, right? Then it becomes something like this. See? G09, that's equal to this. G0 equal to what? This, and then you see here, okay, this one is what? D1, this is D2, D2, okay. And then you'll see, since the QV minus EG, since the EG is so small, that QV minus EG should be what? Big, right? It should be what? Should be positive, right? When it's positive, you see this, denominator is 1 kT, here denominator 2 kT. Now you know what? Which is bigger? I think here's the opposite, okay. I think this is bigger, right? Because the KT on the denominator is smaller, right? It's positive, right? So that power is bigger. That power is bigger, so this is bigger, right? Now if you compare this one, this one dominant, right? This one dominant. So you know that what? You know that in the germanium diode, right? Germanium diode, right? The 1 KT dominant, right? So that n equal to 1, right? N equal to 1, okay? That's it. This is why n equal to 1 here, okay? For germanium, okay? And then you can do the similar things, for what? For gallium arsenide. We'll talk about silicon later, right? For gallium arsenide, you can do similar things, right? This is 1, this is 2, and you plug them together, is this, right? You can get rid of this guy, get rid of this guy, okay? Then the problem here is what? You can assume that it's minus Eg over Kt. Here's minus Eg over 2 Kt, right? Since now the Eg, the germanium, the Eg, the band gap is what? It's 1.44 eV, right? That's a pretty big. That's pretty big, okay? When that's so big, right? So the large lective, right? Think about this, okay? Uh, but this lective, right? When this lective, you know, the denominator is bigger, and then this guy is bigger, right? This guy is bigger, okay? That's why he is bigger than him. So when you think about the two process, two possibilities, so the bigger one dominant, right? That's why big one dominant. So that's n equal to 2, right? N equal to 2. So that's basically tell you if you use, gas aniline, arsenide to make a diode, you will see the recombination dominant, okay? If you use germanium, you will see diffusion on the p dominant, right? And then since the germanium band gap is 0.6, this one is 0.4, right? Now you may care about, what about silicon? Silicon's band gap just between these two, right? Between these two, okay? And then when you study this, you figure out that the silicon is interesting. Silicon depends on quality, right? If the quality of this depletion region has high quality, they will go with n equal to 1. If they have low quality, they will go equal to n equal to 2. Why is that? Because the band gap is close to QV. The entire thing here is small, this is small, they kind of equivalent, similar, comparable, and then depends on quality. If the quality, physical quality of the silicon diode, if one has higher quality than others, then either diffusion, if the quality is higher, your recommendation is smaller, right? And then you what? Your diffusion dominant. If the quality in the depletion region is low, you have a lot of recommendation, and that recommendation dominant. Okay, so that's about the analysis. Let's here talk about the same thing. Let's talk about the same thing about the, especially for the recommendation, right? For the this recommendation, this is diffusion. You can read these slides if you're interested. Okay, so okay, with that, if you want to know, if you have both diode, I think we talk about this. We also discuss this in the electrical equivalent circuit, right? When we discussed this a few days ago, beginning of this GIAN class. Then if you know your G09 is 10 power minus 12, and then G02 10 power minus 9, then this is D1, right? Your D2. And when you plot this, you basically will see two slope, one slope here, slope here. And then typically the slope, when the slope get more steep, that is 1 kt, okay, 1 kt. Because this V is here, I is there, okay, kind of reverse, right? That means more flat shows more what Vi will be more steep, right? Because V and I with x-axis, y is y-axis, okay. So here when it's more flat, that tell you recommendation n will be get closer to 2. When it's more what steep, so that will be the diffusion, okay. That n to get close. Plot it by itself. You can plot it easily by itself. So that's about the diode. So next thing, so far we have talked about the diode, only talk about the diode function like a diode, right? We have not add any what photocurrent, right? Any photo generations, right? So next thing we're going to add is a photo generations, okay? about the photo generations, right? So that's basically, we still use a diode, but now the equation changed because I have generations there, okay? I have generation and also I have recombination, right? So this come to continuity, right? Continuity equations for electron, right? Basically, the diffusion coefficient times the gradients of this, electron, right? Then on the p side, right? The diffusion coefficient of these minority electrons. Then also their gradients, right? The gradients of that equation of that electron minority, right? And then this give you what? The diffusion rate, how fast the electron diffuse. And then you have generation, right? And they have also generation. What does the generation mean? Generation means you under sunlight, you generate extras, right? That is different from the inject electrons from the inside, okay? And then now since you have what? You have a lot of extra electron holes there, and then you have a recombination rate, right? So here, these are general equations. Diffusion, how much carriers diffuse into the region, how much generated in this region, how much recombined in this region. So the diffusion plus generation, these are positive. And the recombination is the loss mechanism, is negative. Okay, that's why it's not like this. Okay, so with that, okay, now let's understand what is generation, right? So under the sunlight, the generation basically is what? It's the light absorption, right? So if you think about this is the top surface, and then this inside, your device, this is inside your fumes, and then the sunlight pass through, Remember, if I just see during this delta x, depths, this delta x depths, how much electrons I can generate. That's basically if you consider the quantum efficiency 100%, it is what? One electron generate one electrons, right? One photon generate one electron, 100% equi, okay? So with that, that's basically the electron generation by photon is by the absorption, right? By the absorption. Let's see, typically if you know that if the photon, the light have intensity of I as go deeper to some regions, that light intensity will reduce, right? Reduce to what? I9 times e power minus alpha x. That alpha is absorption, right? As you pass through the material absorb you. So that's why when you get out, transmit it out, you get less intensity. That's about the intensity. And also you can do something for what? For photon flux. That's the photon flux. So the photon flux is the same thing. It's the number of photons per centimeter square per second, okay? That's also multiply e power minus alpha x. With that, you can see that here, when my photons come into the fumes, there's reflection R, right? So what if I ever get inside will be 1 minus R, and then multiply what? And then this the BS lambda, e power minus alpha x, because here's x, look at that, here's x. Because I already passed through the x distance, that's why how many remains there is, how much initially comes here, and then multiply that, okay? That's it, okay? And then that's for what? That's for this side. That's for this side. See, for the x. When you get to x plus delta x, get this side, you see what? You see the same equal 1 minus r, and then multiply bs, and then exponential minus alpha x plus delta x. Alpha, that x positive. Here's x plus delta x. Okay. And then if you are asked, how much light absorbed in this region, then basically, this incoming light minus the outcoming light. This incoming light, subtract, not multiply, okay? Incoming subtract the outgoing one. Then that's how much we absorbed, right? That's basically what happens here. Look, this is incoming, right? This one multiply that is outgoing, right? That's why you put them together. This multiply this is incoming, outgoing, right? And then since typically this one is so small because we now differentiate this cyclic, right, to very small cyclic. Then you can see that is too small. That's 1 minus e minus x. That's so small, you can just see that's equal to 1 minus x, right? So that's 1 minus 1 minus alpha lambda delta x. Then what you see here is This is generation. The photo flux, then you just subtract that reflection and then multiply this e power z and then this absorption coefficient times delta x. Okay, that's it. This is the generation rate. And see gxr, that's this. Okay, that's the generation rate. And that one can be plugged well here. See here. Plug this. This one to there. Okay. Now you get figure out how to find the. So with that, I think there's a few minutes left. I probably will talk about this in tomorrow's. Okay, my time will be tomorrow. You guys will be tonight. Okay, because the next chapter will be short, so it's good to leave some information here. These are very important, basic, fundamental information. I would like to spend more time here. Tomorrow. Okay, stop here. We have a few minutes. We can take like 1 or 2 questions here.
Thank you, sir. Participants, if you have any question, you can please raise your hand. Mr. Said, you can ask your question.
Yeah, hello.
Yes.
I'm audible, sir?
Yeah,
Yes,
I can
yes,
hear you.
you are.
Yes. So I have a question from the slide 55.
55.
Yeah, 55.
Yeah.
Yeah, how we are getting this effective diffusion length of that carrier?
How you get this?
Yeah.
This probably I would suggest you take some reference. They will give you very specific details how they derive this.
Okay. So as we have seen that in the numerical, so sometimes when the surface recombination is less, so the diffusion length, effective diffusion length is more than the thickness of that layer. Is this assumption is correct?
See, this is short diode, right? Short diode, the effective diffusion length should be longer than the thickness. Is that your question?
Yes.
Yeah, that's true.
No. Effective diffusion length is larger than the thickness. Is this assumption is correct? Because even the diffusion length maximum should be the thickness of that layer.
No, that's not true. The electron has its own effective diffusion length or has its own diffusion length. That diffusion length can be thicker than the thickness. That your thickness has nothing to do with the electron's own diffusion length.
Okay, thank you, sir. Can we
No
get
problem.
any reference regarding that one for finding the effective
For
diffusion
this,
length? Yes,
this
yes, yes,
I
yes.
will try to see. You can Google this. I this is a very common sense. Just
Mhm.
diode, right? Why not you search it first, and then if you cannot find, let me know. Okay, you should be able to find this easily. This is very common. Okay,
Okay, sir.
great.
Thank you.
Yeah. Okay, any other
But
questions?
as of now, sir, I cannot find any. Participants, if you guys have any question, you can still raise your hand. We have 1 more minute. Otherwise, we'll close the session. I guess we don't have any questions. Maybe they can
Okay,
ask
great.
later.
Yeah.
Thank you, sir.
Great.
Thank
Okay,
you.
no problem. Thank you.
Yeah.
Bye bye. Yeah.